Oh yeah, sorry, I forgot to warn people. If you have your cameras on and you want to be on the recording, this is the time to disappear. Okay. So hello everyone. Thank you for coming to the second SPAAM seminar of the term. So our first speaker today is Simon Gabriel. Simon's a second year CDT student from the CDT mathematics student, right? Yeah. And he'll be talking today about hierarchical structure in a condensed zero range process. So thank you, Simon.
Thanks, Diego. Thank you for having me today. So yes, I will talk about condensation in particle systems. So maybe first of all, a bit of motivation. I guess you don't get around that. So stochastic particle systems, I guess it makes sense that they somehow come from, well, particle physics. So what we normally think of is we have a box, let's say a box here, which we denote by lambda. And in this box, we have some particles. So these are these pink dots in here, and they move around independently from each other and maybe interact a little bit. And well, let's, for example, think about some water vapor in a gas chamber. And the higher the density of this of the water molecules is, at some point you will form droplets, and actually water will form. And this process is called condensation. So you see also here a very nice picture of condensation on the window, which I'm pretty sure everyone in the UK saw at least once. And what we will actually be looking at is a discretization in space at least. So normally you have a continuous time space. So we will look at a discrete version of this. So you can just think about a grid, and our particles will move around on this grid. And they, well, one of our assumptions is they only interact with each other if they're really on the same position. And well, that motivates why we want to look at condensation, and we would actually like to understand it in a very simple setting. And one of the easiest settings is the zero range process. So that's a very easy to describe process, but still interesting because you see interesting phenomena, for example, this condensation. So the zero range process is a continuous time Markov process on a state space of L vectors, which take integer values. So here L is now, well, I told you we think about somehow, for example, a grid. So L is now the number of grid nodes that we have. Or if you rather like, you can also think about a discrete torus as I drew it down here. So down here, if you, for example, have L equals 6. Or also you can think about a complete graph. So the geometry doesn't really matter here. It's not too important. And configuration in this space here looks as follows. For example, for this configuration I drew here at the bottom, we have 6 sides and we have 7 particles. So now if you go to the first 2 sides, we don't have any particles on them. For the third side, we have 2 particles on them. For the fourth, we have 4 particles on them, and so on. So the infinitesimal generator for this Markov process is given as follows. So for everyone who's interested in this, for those who may be not so familiar with generators, I maybe just quickly explain what the dynamics of the system actually are. So think about you have some exponential clocks on each of those sides, and these clocks are, well, exponentially distributed, and their distribution depends on the number of particles which are on this side. So for example, in this case, on the fourth side, we have 4 particles, so we'll put U4 here. So this is the U, the same U as is in generator. And similar, for example, for the second side, we will have an exponential, which is U2 distributed. So you have now L of these clocks, and whichever clock rings first, we take a particle from this side and we move it uniformly at random from some other side. So let's say clock rings here first, we take the topmost particle and we move it uniformly at random to any of the other sides. But this actually doesn't matter. We could also choose nearest neighbor interactions as long as we're irreducible and symmetric. And okay, clearly, if we don't have any particles on a side, we can also not jump. So one of our assumptions is that our rate, if we don't have any particles on it, is actually 0. So interesting property of the zero range process is that it preserves the number of particles. So if we start with a certain number, let's say 10 particles, even after time n, we will still have 10 particles. Nothing really changes. So this actually motivates to introduce this finite subspace of our state space, which are all configurations that conserve the number of particles. So in this case, our number of particles we denote by n, and well, it's basically all vectors up here that sum up to n. And we want to study, or what we are interested in is the limiting behavior of these processes here as L tends to infinity, but also n tends to infinity. So we take the number of particles and number of sites to infinity, but not in any way. We want to take them to infinity in such a way that n divided by L converges. So here, n divided by L, you can think of a density. So n is the number of particles, so you think about it as mass, and L is the number of sites, so think about it as the volume. So mass divided by volume, you get the density. So that's the idea behind this. So we make our system bigger and bigger and bigger, and we put more particles in the same ratio. And then we actually want to see what's happening. So how do we study these systems? Well, we want to study their stationary measures. And the stationary measures on these finite process or finite spaces, these rho n's, where we conserve the number of particles. So we have n particles in there, are actually quite nice because it's an irreducible Markov process on a finite state space. So we have a unique stationary distribution. And this stationary distribution we will denote by pi ln. So these pi ln's we can calculate explicitly, and they have this following product form here. So this is a product form, that's how I call it, it's not a product measure. So first of all, we have this 1 over sad ln here, so that's just a partition function. Think about it as a normalizing constant, so we have a probability measure, so we actually don't worry too much about it. And then we have these w's here, which we call weights. And these weights we can actually calculate in terms of the transition rates in our generator, which is what we have below here. So what you should think about the weights is a measure of attractiveness. So let's say W1 is very large. What does this mean? Well, let's take a single site, and W now tells you how attractive certain particle occupations are. So how attractive are 2 particles to be on you, or for how attractive is it for you to have 2 particles on you? How attractive is it to have 5 particles on you? So if W1 is very large, that means it's very attractive for you. So we try to get a particle as quick as possible. On the other hand, if W2 is very small, then it's a very unattractive state. So let's assume you have accumulated like a particle, and now a second particle jumps on top of the first one. So what will happen is that the site will almost immediately repel it, want to get rid of it, because it's a very unattractive state to be in. So that's how you should think about these W's. And in fact, there's a one-to-one correspondence between the weights and the rates. So one way already, we have this formula above here, but actually works the other way around too. So if I give you certain weights, I can actually calculate transition rates up to a multiplicative constant. And because we are only interested in the stationary distributions of our systems, in the following we will only talk about weights and not about rates anymore. Because these are basically the things that determine our stationary distributions and will also determine our dynamics. So talking about condensation, we need to formally define it first. So let's look at this single site marginal here. So what does this probability measure here mean? Well, we look at the number of particles on the first site, and instead of the first site, we could choose any site. So we could also choose site X here. It doesn't really matter too much because we are a homogeneous system. So if we recall the generator, our rates U, they don't depend on the position. They don't depend on the site you moving from. They're always the same. So it actually gives us very nice symmetry here. So just for simplification, we choose the first site. And this is now the distribution that in a system with L sites and N particles, we will, how many particles, or what's the distribution that a certain amount of particles will be on this site. And one of our assumptions is that this has a weak limit. So in the sense of probability measures. So we converge in distribution, and this limiting distribution we denote by a new rho. So the rho here is again the density that we choose to converge to. So n and L, or n divided by L, converges to infinity, as they both themselves tend to infinity. And we converge to this measure. So if we just look at the mean occupation number of a single site. So pi ln of eta1. What does that mean? It's basically the expected number of particles that we see on a single site. And because we have a conserved number of particles in the system, also in the mean, the number of particles will still be conserved. So we actually know that this is equal to n divided by L. And well, as n and L tend to infinity, this converges to rho. On the other hand, because the identity here is not a bounded function, so it's not a valid test function for our convergence and probability, for our convergence of the distribution, we cannot really expect this equality to also hold in a limit. And we actually might have a strict inequality here. So this is possible. And so what does this mean? So we have our finite systems where we have a density of rho in here. So we have, if you want, rho particles, or we have rho times L particles. Now, as you go to the limit, somehow some particles vanish, but it can't really be on any finite sites, right? Because finite sites, you could all observe them in the limit, because those would be, if you take any finite number, it's going to be a bounded test function. You can just take the cutoff. So because they're also positive, they kind of need to diverge. So our number, or the occupation number, actually needs to diverge in the limit. So that means there are some particles with infinitely many, some sites with infinitely many particles on them. And well, this is basically what condensation means. So just to give a proper definition again, so under the above assumptions, which was just that this weak limit here exists, we have a system that exhibits condensation precisely if we have a strict inequality here. So with some particles, we cannot observe in the limit anymore, and that means they have to be somehow on sites with diverging number of particles. So now the question is, we have different kinds of infinities, obviously. We could converge, or with what rate do we go to or diverge to infinity? We could go diverge in terms of the system size, maybe square root of the system size. So I think it's very important to talk about scalings. So let's again look at the occupation number of the first site, so eta1, and rescale it by n to the power gamma. So gamma is now just a real number in a unit interval. And let's look at the two boundary cases. Well, gamma equal to 1, we have a denominator here of 1. So we just get the occupation number itself. So it's just a number of order or magnitude 1, so 1, 2, 3, 4, 5. And we call this the microscopic scale. So this is the scale where we defined our dynamics on, for example, in the beginning. On the other hand, if we choose gamma equal to 1, we will renormalize here with n, and we will get the macroscopic scale. So there, for example, if eta1 divided by n is a positive number, that means a positive fraction of all our particles will be on this side. And clearly, you can also choose any intermediate scale here, so any gamma which lies in between 0 and 1, and we call it intermediate scales or mesoscopic scales, but they're not really too interesting for us. So one of the standard behaviors that you will find in particle systems on the zero range process is that if you have condensation, then you have condensation on a single site. So what does that mean? Think about this torus, for example, I had in the beginning. So you had some particles jumping around there, right? So they might jump around. So now you take the limit and you zoom out at the same time. And as you zoom out, basically a torus, well, it will become densely populated because you also take the volume to infinity. But since you zoom out, it eventually just looks like a point. And then you will have a single spike here, which is basically the site which has n particles on it. So all the particles. So that's a very normal behavior that you often see. So now the question is, maybe we see something more interesting. So instead of having like a single spike, we maybe have some more spikes here of different lengths. So what do we need to do to see something like that? And one of the things that you can do is to actually tune your jump rates. So remember in our generator that we defined in the beginning of the zero range process, we had u's here that didn't depend on the size of the system. So it didn't depend on L. So now as soon as you tune also your rates, which is equivalent, as we talked about, is tuning your weights, you will actually see more interesting behavior. And the kind of behavior that we want to, or that we're interested in this talk, is a condensate which is distributed with respect to Poisson-Dirichlet. So Poisson-Dirichlet distribution is a probability measure on some infinite dimensional simplex, or actually the boundary of the simplex. So, well, it's just a vector which is indexed by the positive integers in decreasing order, takes positive values and sums up to 1. So if you want to, you can think about it as a probability measure on the integers, just that your probabilities are decreasing. And there are multiple ways to characterize this distribution. One of the standard ways is to choose stick breaking procedure. So stick breaking procedure works as follows. Poisson-Dirichlet distribution is actually a one parameter family, so we have some theta here, which we actually don't mind too much. Let's just choose theta equal to 1 for simplicity, because I'm also running a bit short. And then we choose infinitely many random variables, which we sample IID. And these are beta 1 theta distributions. So in case of theta equal to 1, these are just uniform distributions on the uniform interval. And what we do now is we take a stick of length 1 and we break off a piece which has length u1. And now we take the remaining piece, which has now length 1 minus u1, and we break off a piece of u2. And we again are left with a stick which has length 1 minus u1 times 1 minus u2. So now if you go on like this and eventually you reorder your sticks in decreasing length, so if you just put them down and you order them in decreasing order, this will be distributed with respect to a Poisson-Dirichlet distribution. So in the case with uniform distribution, this will be a Poisson-Dirichlet 1 distribution. So in fact, there's actually a limiting procedure. So you actually break your stick n times, you reorder it, and then you take the limit to infinity of these distributions. And okay, just a quick notation. So if you have a configuration omega eta and omega ln, so L sides with n particles, we can write this eta hat for the reordering. So now we just reorder our configuration. So on the first index, we have the largest occupation number, so the largest number of particles we will observe in the system on one side. Second index, the second largest number. Then a recent result by Paul Stefan and one of the former PhD students, where in fact I only state a bit of a weaker version here. Well, you choose a theta arbitrary positive, and then you have a zero range process with weights of this following form. So we have these WLNs here. So now our weights depend on the system. And I will talk about these weights a bit more in the next slide. So just think about it as a generalized binomial coefficient for now. So if you now look at the reordered version of these sites, of the occupation numbers, so just think about, we have our occupation numbers, we reorder them on a macroscopic scale, so we divide by n. Then it in fact turns out that we converge to a Poisson-Dirichlet distribution. So if we reorder our condensate, it will look like a Poisson-Dirichlet distribution. And this is not all it tells us, it also tells us that it has all the particles in the condensate. So there's nothing on any other scales, on an intermediate scale, on a microscopic scale. So now talking about these weights, we have this specific form here with the gamma function. So for example, if you plug in n equal to 0 and for arbitrary L, then this will be actually equal to 1 always. Whereas if we choose any positive n, this will decrease rapidly towards 0, and it decreases faster and faster as we choose L larger. So what does this mean in terms of the dynamics? So remember, we have the equivalence with the U's and the W's. Well, for 0 occupation, we will never jump because we don't have a particle. But then we have a peak here, so very high jump rate, and then it goes down to 1. And this peak here will actually increase in L, which means the larger L is, the more likely it will repel it. So remember when I talked about these weights, when there's an unattractive state, it tries to repel it. So in this case, the unattractive state is having one particle on a side. So you don't want to be in that, and the limit, you basically immediately get rid of this particle. So two interesting observations. So first of all, if you look at the stationary measures now of our process, well, remember we had an explicit form, so we can just write this down. And maybe some people know how it looks like. It actually turns out this is a Dirichlet multinomial distribution. And I didn't tell you that, but that's an equivalent definition how you could define a Poisson-Dirichlet distribution as it was originally done by Kingman. So if you take the limit of distributions like this as L to infinity, well, you converge somehow to a Poisson-Dirichlet distribution with parameter theta. Obviously, it's a bit more subtle, but so it's not at all surprising that we see a Poisson-Dirichlet distribution in the condensate here. On the other hand, the asymptotic behavior of our weights looks as follows. So our weights for very large n will basically look like theta over L and n inverse. So we get this theta over L, we get from this gamma function up here. And then the top part here looks kind of like an n minus 1 factorial. So we have an n left in the denominator. And well, because we have a condensate, so our scale that we're actually looking at, n will, well, the occupations that we will be interested in, n is actually of order n, large n, so of the total number of particles. So in fact, choosing our weights according to this rule here should only matter on a macroscopic scale, so only for large enough n. And below that, we could choose anything, but as long as we choose it for a macroscopic scale, we should see a Poisson-Dirichlet distribution. And I think I'm running a bit out of time, so that's why I'm going to skip the proof and then next and just finish quickly with the last slide. Generalization of this, what I just basically mentioned, so is work in progress together with Paul and Stefan. So as I just said, our weights in the above case look somehow something like this. And this should actually only matter on a macroscopic scale to see a Poisson-Dirichlet distribution on the macroscopic scale. So again, we consider a zero-range process. We have size-dependent weights. The first assumption here is a bit technical. You can just ignore it. That's basically replacing these reconvergence. We can actually talk about condensation that we had in the beginning. The second statement is the interesting one that you actually want to look at. So what we have here is that if we choose, they exist in intermediate scale. So this is some ALs that diverge to infinity, but if we rescale them with L, they converge to 0. So it's an intermediate scale. And for every weight above, or for every occupation number above this intermediate scale, if we look like, approximately like the weights that I just wrote down, which is precisely this identity here, if you rewrite it, then you see a Poisson-Dirichlet distribution. That's exactly the same statement as before. However, now it's not so easy because we have here the subindex 0 alpha. So normally you would look at a Poisson-Dirichlet distribution on the unit interval. But now, since we only have assumptions on our weights in the macroscopic scale, we could basically choose weights very, very crazy on every intermediate scales and microscopic scales. And it's actually not to be expected that all our particles will be in the condensate. We might have different phases where they will concentrate on, so different scalings where we will see them. And that's precisely this alpha here. So that's the number or the fraction of particles that will actually be visible on a macroscopic scale. And this is determined by the limit here on the right-hand side in 0.3. So that's a second moment assumption that we actually have a scaling or that we actually see something on a macroscopic scale. It's a bit of a technical thing still I try to get rid of. But yes, I think I run a bit over time already, so I just stop here and thank you very much and hope you have some, if you have any questions, please let me know.
Okay, thank you, Simon, very much. Before I stop the recording, can you maybe a round of applause for Simon? Okay, now I stop the recording. We have some time for at least 1 or 2 questions if people want to ask